this is a topic that we've talked about already, the integral as a net change. So if we want to know how much some value or quantity changes, we can use a definite integral to do that. We just need to know what the rate of change is. So if we know how fast something is changing, we can use the integral to figure out how much it changes over a certain period of time. And this is really probably the most important application of an integral, is being able to figure out how much something changes over a period of time. So we're going to look at a few examples here at how to do it, and we're going to look specifically at some motion examples because motion is a good application of this topic. So we'll start this with an example here. We have a particle moving along a line, and for single variable calculus, the calculus that we're doing, motion along the line is about as good as we're going to get until we get into parametric equations in a few weeks. So we're moving along a line right now, and the initial position is at 9 centimeters. So if you picture like the x-axis, we're at 9 centimeters, or at the 9 on the x-axis to start with, and we know the velocity at any given time. And the velocity is given by that function there. Our goal is to figure out, if we start at 9, where do we end up when t equals 1 second, and where are we when t equals 5 seconds? If we take the integral of the velocity function, the definite integral from 0 to 1 of that velocity function, then we're going to figure out how much that particle's position actually changed. We're going to figure out its displacement over that time. So the way we'll set that up for part A, it's going to involve this integral here, the integral from 0 to 1 of the velocity function. I'm just going to write it like this right now. Okay, now this integral right here is going to tell me how much its position changes, but it doesn't tell me where it actually is. What do I need to include in this to figure out where it actually is? Cole? What constant? Yeah, we need to include where it started. So we're going to start at 9, and then we're going to move by some amount here. So our position, and I'll call this S of 1, is going to be where we started plus the change from where we started over that time interval from 0 to 1. Now, this is an integral that you should be able to evaluate analytically, so let's go ahead and do that. It'll be good practice for us here. So I'm going to replace this v of t in my equation with t squared minus 8 over Yeah, if we rewrite this as t plus 1 to the negative 2, then that's going to make it easier to evaluate the integral. So let's go ahead and do that real quick. So I rewrote it here, and I made a couple of changes. First of all, I split the terms into two separate integrals. So I've got the t squared here and the 8 over t plus 1 squared here. I pulled the 8 out front of this integral, in fact the negative 8, and then I rewrote the exponent as a negative exponent, and that's going to allow me to integrate that or find the antiderivative fairly easily now. How would I find the antiderivative of this, of the t plus 1 to the negative 2? So if we substitute there u equals t plus 1, then du is going to equal what? Yeah, 1 dt. So basically I can just replace that with a, sorry, that should be a u. Replace the t with a u there, and replace this whole thing here with a u there. And then I should replace those limits also if I'm going to do that. So instead of a 0 as my lower limit, I'm going to have 1, and instead of 1 as my upper limit, I'm going to have 2. In this particular problem, since du is equal to dt, it actually wouldn't be too bad to evaluate this integral leaving the t's in there. But I like the substitution. I like the substitution because it simplifies it a little bit for us. All right, so let's move on then. We're going to have 9 plus, what is the antiderivative of t squared? T cubed over 3. We're going to evaluate that from 1 to 2. Minus 8 times the antiderivative of u to the negative 2, which would be what? Well, it would be u to the negative 1 divided by negative 1, right?
Yeah.
And when I divide by that negative 1, I'm just going to change the sign on the 8. Sorry, I made a mistake here. This lower limit should still be 0, and this lower limit, or upper limit, should still be 1. Thanks, Ethan. We'll evaluate that from 1 to 2. So then that's going to give us 9 plus, here we get 1/3 minus 0, so just plus 1/3, plus 8 times, well, 8 over 2 is going to be what? So we're going to get 4 minus, and then if we put 1 in here, we get 1 over 1, so that's just going to be 4 minus 8, right? So it's going to be negative 4 times negative 8 is negative 32. 9 minus 32 is negative 23 plus 1/3. And what are the units going to be? Yeah, we're looking at a position on the line, so it's going to be negative 68 over 3 centimeters. What I'd like you to do right now is confirm that with your calculator. Okay, and it made another mistake here, sorry. This 8, we used the 8 already, so that should not be there. So that should just be a negative 4. So we get a negative 4 there. 9 minus 4 is 5, plus 1/3 is going to give us 16/3. Is that better? Or 5 1/3 centimeters? Whew. What do we get for part B? Part B should be very similar, except we're evaluating from 0 to 5 instead of 0 to 1. And what'd you get for that? 44 even? You guys agree with that? In this problem, we're looking at where something starts, and then we're taking an integral to figure out how much it moves from that starting point. So to figure out where it ends up, we take the starting point plus how much it moved, which is given by the integral of the rate of change. In this case, the rate of change is the velocity. Just a couple of terminology things here, some formulas that are useful. Displacement is simply the change in a body's position. We usually represent displacement with the letter S. And to figure out how much something changes, if we're looking at the velocity or we know the velocity, we can figure out how much it changes in position by integrating the velocity from the starting point to the end point. We talked a little bit, well, if we want to use displacement to find the position like we did in that example, we start at the starting point. In this case, this was our origin here where we started, and then we integrate from that starting point to our ending point, the rate of change, the velocity here. So the position at any given time can be given by this formula here. Does that make sense? But we can use this idea of integrating a rate of change in other ways besides linear motion. So we saw it in linear motion with velocity, using velocity and integrating it to get position. But we can also use this idea for any rate of change to figure out how much anything changes. So we're going to finish with another example here. We're going to finish with this would be kind of an economics, social example. This is actually It sounds kind of silly, but it's an example that would be important to an economist in this particular country, especially somebody who's looking at the agriculture. So if you can model how many potatoes are going to be consumed by the country, then you have an idea of what your farmers are going to need to produce. And this will be important to set prices and stuff like that. So what we have here is a function that tells us how many potatoes are consumed each year, and we want to know how many total are consumed over this time interval from the beginning of one year to the end of the next year, so over a 2-year period. Before we get out of here, I'll let you evaluate this on your own, but I want to get the integral set up to do this. So the rate of consumption is given by this formula right here. So if we want to know the total consumption, what could we do? Okay, so Willie says we're going to integrate the function c of t. So we're going to integrate this rate formula, or this rate equation. And what are our limits of the integral going to be? Now remember, we're going from the beginning of 1972 to the end of 73, and we're defining t as the year since the beginning of 70. So at the beginning of 72, what's the t value going to be? 2. And at the end of 73, it's going to be 4. Okay, because the end of 73 is the beginning of 74. So if we evaluate this integral here, we're going to be able to figure out how many total potatoes were consumed over that time interval. I'm going to let you go ahead and do that on your own. But like I said, this could be a really important thing to know for somebody in studying the economics of a government or in the government and making policy decisions.